Hello, it's Keith here, and this is lesson 2 of the so-called ChibiTracks assembly programming tutorials on the 68000. Now, ChibiTracks is a multi-platform music player I've written. You can hear it here, you can see it running on the Genesis, and basically we're going to look at part of the code today. Now, the first of the lessons, if you will, in this series is actually part of the Z80 series, because the music files themselves can be played on any system. The binary file that plays on a Z80 system is the same binary file that plays on the 68000. And so in that original episode, we looked at the source code for one of the files, and as I say, it was a Z80 source. Now today what we're going to do is we're going to start looking at the tracker itself, and we're going to look at the parts of the Z80 source that are being played, but it's actually the binary file we're using today in actuality. But so that we can see the data that's being read in and processed, we're going to look at the Z80 version. Now the important thing to bear in mind is that ChibiTracks was designed so that we could play the same binary file on all the systems. The Z80 is a little Endian system, but the 68000 is a big Endian system, and this means that the internal structure of the file is in little Endian, and it's also using 16-bit addresses. For that reason, we're going to have to read in the little Endian addresses and swap them, and we're also going to have to treat them always as offsets to the actual song address because they're not full 24-bit. Now, offsets and relocatable music files was an option on the Z80 and the 6502. On the 68000, it's a necessity because, as I say, the address internally in the file is incomplete. Anyway, let's go over to our source code and let's take a look at the parts of the code we're going to be looking at today. So we're going to be looking at the ChibiTracks source, which is the multi-platform code. This uses a sound driver called Chibi Sound Pro, which is platform specific. There's other tutorials covering the content there. Now, each of the channels has a basically a block of data that defines its current state. Now, I've got one of them viewed here. This isn't the actual one that's used. This is a sort of template that was used in an early version of the code, but it's the same format, but there's no initialization anymore. It's all initialized from 0. But this is what basically, this is a sort of an example of the data that we have. So we've got a byte for the note number. I've got a byte for the volume, 255 is the loudest. A byte for the channel, that should be 0 on channel 0, 1 on channel 1, and 2 on channel 2. And we'll need to initialize that later on. We've then got a byte for the pitch shift. We've got a 32-bit long address for the playing instrument, which is in this case the silent instrument. The silent instrument is just an empty instrument basically to stop the current playing sound. We've got a timeout, which is a byte for the current playing instrument. We've got a timeout for the current playing pattern. We've got the address, which is a long of the current pattern. That's just a 0 here, but that will be initialized by an init routine. And we've got an address for the current position in the sequence, and the addresses are all 32 bits. Now, they were 16 bits on the other systems, and for that reason, the channel layout is actually different on the 68000 to the Z80 and 6502. It was the same on the Z80 6502. It's also bigger on this system. It used 16 bytes on those systems. It uses 32 on this one because of those longer addresses. Now, all of the data is read in from a music file. Now, we've got an assembly file here that has not been converted to binary, but the one we're actually playing from today is binary because this is Z80 format code. But basically, the internal structures, like the My Song pattern list address here, this will point to the actual list of patterns. Where is it? Down the bottom somewhere here. Here is the actual pointers to the patterns. And here are the patterns themselves, and so we're going to have to process all of these. Now, the important thing, as I say, is that the addresses in the binary music file are little Endian 16 bits, and so we're going to have to convert those in real time. That's what the 68000 is having to do, the extra work to cope with the format for the Z80 systems. That was more sensible than re-exporting the music files. That was something I very specifically wanted to avoid. I used Tracker before this. Tracker is a fantastic tracker. It's better than my tracker. It's a better music player than my music player. But one of the things is that, generally speaking, the music files aren't relocatable. And so this means you export from memory address 8000, and then on another system you want to load it to memory 9000, you have to re-export all your songs, and it gets a big pain when you're working on lots of systems, because every time you change a note in one of your songs, you have to re-export the binaries to get the right addresses, and if you don't get the right addresses, it doesn't work. And I think Tracker does have a relocatable song option, but it makes the tracker quite a bit bigger, and it was a bit too big for me already, so that wasn't something I wanted to consider. Anyway, this is my solution. Again, I'm not saying it's the best music player. It certainly isn't, but basically it's what I've got. So basically, when it comes to actually addressing the data within the channel information, we have these pointers to the various bytes. Now pattern L is the low byte of the pattern address, so that's the first byte of the 32-bit value there. There's no H or anything, we just use the L parts. These again to mimic the Z80 version, but because we're on the wonderful 68000, we can load in entire addresses in a single command, and we will certainly do so. Now, one thing that is optional is the ability to change the speeds. Again, not really as important on the 68000, but on the Z80 and 6502 limited performance systems, multiplying the speed to change the speed of the song was a nice thing to have, but potentially a luxury we couldn't afford, and we might want to save a little bit of memory in the source code, so we could disable it. But this basically allows us to change the speed of the song at playback time. The alternative is to pre-multiply the song speed. For example, the Chibi Akamas theme is designed to play at a speed of 5, and that means that each of the lines in the pattern should wait 5 ticks. We can either do that at the playback time, and we can multiply up those ticks, or we can export it in the binary and pre-multiply it effectively. And that means we can disable this speed multiply option and make our player faster and smaller, but it means we can't change the speed, and we might want to change the speed if we're playing the song on a 50 Hz system one day and a 60 Hz system the next day, because the 60 Hz system, the interrupts are likely to be just 1/6 faster, so maybe we want to change our song speed to compensate. Anyway, that's up to us. Now, the first thing we do when we start our song for the first time, we need to set the song base, and we need to set the song base to the address of the song binary in memory, and because all of the data is going to be loaded in from that. Now, the start song, the very first thing we're going to do is we're going to actually wipe the entire channel state data. So the channel state data here is we're going to start pointing to the first channel, and we're going to basically wipe all 3 channels. We're going to first wipe them all to 0, which is the default state for the channels, but we need to set the channel numbers, otherwise the data passed from ChibiTracks to Chibi Sound Pro will all go to the first channel, channel 0, and that will ruin our music basically. So we're writing the channel numbers directly to the channel number value for each of the channel data entries there. Now, there are a few other things we need to set up for the channels to work correctly, but they're actually all done by the following routines. We set the instrument to the silent instrument, and we set a valid pattern and sequence. That all happens anyway, so we don't need to worry about it here. Now, from that point, we are going to actually start playing our song. Now, we're setting D0 to 0 here. D0 at this point is actually the entry in the sequence that we want to play from. Now, the first time we play our song, we're going to start from sequence 0, but we might want our song to have an introduction and then loop back to a different position in the sequence. Now, the sequence is this sequence of numbers, and these numbers are the various patterns. So an entry of 0 here is pattern 0, an entry of 1 is pattern 1, and if you can't guess what the entry 2 does at that point, I think you're probably watching the wrong tutorial series, because hopefully it's pretty obvious. Anyway, so that's what the sequence is. It's the sequence of patterns that we're going to play, and this D0 would be an offset within that. But before we do that, we're going to load in the other data. We're going to basically initialize things. So what we're going to load in? Well, we're going to load in all of this data here. So we're going to load in the number of channels. It should always be 3 at this stage. The repeat point, which is for when the song has ended, that's there. The song speed, as I say, this song is 5, but we can actually change that after we've loaded it if we want. The song load address, this is the address once this has been exported as a binary that this was intended to be loaded from, and we need this to calculate the relative offset for things like the pattern list and the instrument list, and we need to do that for this system because it's a 16-bit file but it's a 24-bit system. So the pattern list and the instrument list has pointers in this header to point to the vector tables for the various sequences for the patterns and instruments, and we then got pointers to the sequences as you can see those. Sequence 0 is for channel 0, sequence 1 is for channel 1, sequence 2 is for channel 2, and you can see a value of 255 at the end is a repeat basically. So that's what's going on there. Now we're loading in the number of channels here, we're loading in the song speed, we're loading in the compiled song base here. Now you can see we're loading this in 2 bytes. We're loading in the first byte offset by 1, and we're shifting it to the left by 8 bits, and then we're loading in the second byte. This is basically converting the little endian source data into a 16-bit value in our register here. The problem is, of course, is we need our addresses to actually be 24 bits, and so this can only be treated as an offset, and so we're calculating the difference between that and our actual song base, and that is now an offset which we're going to use to calculate all of the relative addresses within our song source data. So the pattern list, the instrument list, and the sequences will all have to be calculated as relative offsets within that data. So we're going to be using that song offset to do that. Now, once we do that, we're now going to start processing the song sequences. So we've basically read in a variety of data there, but what we're doing here is we're basically skipping over the next 3 pointers here. What we're effectively doing here is we're skipping over the song address here, the pattern list, and the instrument list, and we're getting to these sequence pointers here, and we're going to process those and basically initialize each of the channels with the song, with the pattern data. So what we're going to do is we're going to do each channel in sequence, starting from channel 0 here in A4, and we're going to run init song sequence, and then what we're going to basically do is move to the next one by adding effectively 32 bytes there, and that's going to set up each of our patterns on our channels. So here's the initialized song sequence routine. What we're going to do is we're going to load the address of the sequence pointer here, again in little endian, add the offset. We've now got the address of the sequence, and what we're going to do is we're going to add our loop point, which will be 0 the first time, or if we've played the entire song once, whatever we wanted to jump back to. And we're then going to run get next sequence, which will actually load in the sequence from the pointer, because basically we're now pointing to an entry in this, but we still need to convert that to a pattern. So basically what we're going to do is we're going to run this get next sequence, which we'll see in a moment, and then we're going to load the pattern address it calculates into the current playing pattern. We're basically loading a value of 1 into the channel instrument time, and that means that that will hit 0 next time the instrument is updated, which is basically forcing an update. And then what we're doing here is we're loading the silence instrument in, which will silence the channel. Now, the get next sequence routine here will actually update the current playing pattern. We run it there, but we also run it when the pattern ends, and in that case we load in the previous position within the sequence so that we can load in the next pattern number. Now, the first thing we're doing here is we're checking if we've got a 255. If we have, we're forcing a restart of the song. We've reached the end of the song. Otherwise, we've got some debug code here to show what's actually going on. We won't worry about that. But what we're going to do is we're basically going to move 1 byte in our sequence and store the new sequence address there. And then what we're going to do is we are going to basically calculate the address for the pattern itself. So what we're doing here is we're moving to the pattern list within the source data. So we're basically looking for this entry here. Again, it's a 16-bit little endian value. So we are converting that to big endian, and we are calculating the offset there. And then we are basically adding the pattern number multiplied by 2, because the list of patterns is a vector list in 16 bits. So again, these are offsets within our song file to the actual song pattern data, and you can see the song pattern data here. And fun fact for next time, the scripts for the patterns and the scripts for the instruments are identical. It's the same code that handles both, so we either can do either thing, which is quite funny, I think. Anyway, so we are calculating our pattern address. We're calculating our pattern list entry here. We're then loading in our pattern address here, and we are then setting our pattern time to 1, which forces the pattern to update at the next tick, which again will basically mean that it will, as soon as the channels update, the instrument will set to silent because we set that time to 1, and the pattern will update itself because we set that to 1 as well. So this is forcing an update. Now, at the point that this has finished executing, A3 will contain the address of the pattern, and as soon as this returns, we're effectively storing A3 as the pattern address within our channel data. And so that's all there is to that. Now, the final thing we're going to cover here is, of course, when our song ends. What we do here basically is we are fixing up our stack because we've jumped out of playing the song. We're loading in our song base, and we're reading in the byte that represents the repeat point and jumping back to the song start. Now, the repeat point is this byte here. Now, on the 6502 and the Z80, we're actually loading those into memory, but on the 68000, the processing power is so sufficient, I wasn't worrying about doing that, so I'm just reading them in each time from the source binary data. Anyway, that's all we're covering today. We're going to go next time with some more parts of the code. We're going to look at the script processing, which handles the patterns in the music. If you like what you've seen and if you want to see more work done on this music thing, please back me on Patreon. This project, this ChibiTracks software, was written by me as an idea for multi-platform games. I want to make games, I want to make them on lots of systems, but the truth is I have no time to do it anymore. I spend literally all my time writing tutorials and books, so there's no possibility that I'm going to write a multi-platform game that spans more than one CPU at this time. So I don't need multi-platform music software. So if you do need multi-platform music software, you're going to have to think about backing me, because I can't justify spending my time on something I have no use for. So there we go. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.